Hello, GIS students. This serves as your lecture for remote sensing in week 7 of the GIS Introduction to GIS class. So it'll be a little bit of an online lecture slideshow, and we can follow it up with questions in class afterwards. The slides that I'm going to show you here today are kind of building upon some slides that I did for the Introduction to Environmental Remote Sensing class when I taught that last. So in the background here, we can see one of our satellite sensors orbiting over Earth. But then we also see different types of remote sensing done within the Earth's atmosphere using UAV drones over here on the upper right. And then down here we have terrestrial-based LiDAR scanners. And here's some air-flown aerial photography that's been used to make a digital model of the Earth using air photos. So remote sensing, just really simply, is observing objects and processes from a distance using either passive or active source signals, uh, such as electromagnetic energy. So remote sensing systems consist of a platform, and that can be mobile or stationary, like we see in the case of the terrestrial LiDAR scanners, stationary, although you can move it from site to site. As a mobile platform, it could be something that's moving as it's collecting the data. Uh, and that system consists of a sensor, and that can be a camera or a scanner, and or just generally some sort of energy source, plus a detector of catching that energy as it bounces back. And then, of course, we have to have some way to store and process data collected. And then there needs to be, of course, a community, an audience for that data, and we need to disseminate and understand the data as well. So passive versus active systems. So passive systems are the detection of naturally reflected or emitted signals from an object of interest. So a camera, like we see up here with this Sony camera, is collecting light signals in red, green, and blue within the electromagnetic spectrum. So we can see that here, the visible realm of the electromagnetic spectrum. You can see our atmosphere opacity is it's pretty low, meaning that light comes through at these wavelengths of red, green, blue to the Earth very easily. At lower wavelengths, the atmosphere is opaque. Those wavelengths don't get through, and some of those are higher, longer wavelengths. No, shorter wavelengths, and then longer wavelengths also have some areas that are opaque atmospherically. But then these areas where we have what are called atmospheric windows, that's light that gets through to the Earth's surface. And so in those windows, we can use passive remote sensing systems for reflected electromagnetic light. Active systems means that there's an energy source emitted from the sensor, and the reflected energy comes back to a targeted area of interest that can then be detected by the system. So an example would be light detection and ranging, which is usually flown from the air, but can also be from a scanner like we see over here. It emits a laser signal which goes over an area, and then a signal bounces back, and it measures kind of distance to the object that it hits. And so that would be an active system because we're emitting energy rather than just collecting naturally reflected light. So sensors can be quite sophisticated. Of course, you know, there has to be some sort of focal area for the energy that's collected, whether it be reflected, natural light, or if it's some active sensor. It's not always that we're collecting light. We can, in terms of the visible spectrum, we can send radar signals, we can detect gravity, other things. We can do other forms of remote sensing other than light. Um, this can be very powerful because basically we can, from the satellite, we can look at the landscape over a really broad area and really start to understand patterns that are going on. Snowfall, what's the state of that snowfall? And it's just not just at a snowfall site, but over a whole mountain range. So here's an example of a product from remote sensing from within the Earth. So flying a plane over an area and taking air photos. And we can do this in a very traditional sense. Over here on the right, we can see these um, black and white air photos that were collected some time ago. And in that case, the flight of the plane is probably along one of these rows, and it's uh, taking a photo every so often and flying at a certain speed. And then what that means is there's areas of overlap between the photos. If we have more than 50% overlap, then we have two photos covering every part of the land surface. And the really cool thing about this is that with two photos from two different locations, what we call stereo pairs, and you can extract 3D information because we're seeing things from two different angles. And so we can use that to map things in kind of 2.5 dimensions, essentially. Um, in a more sophisticated manner today, we can use drones or from planes, fly many photos with more than 50% overlap in not just one direction, but in multiple directions, and create sophisticated 3D point clouds that are also color information, and use that to model the Earth's surface at a really high resolution. This is called structure from motion, but it's using the same sort of principle as stereo pairs of air photos. And so Dr. Buns does this a lot and teaches about it in that um, geospatial field methods course. So the electromagnetic radiation. Um, so here we're looking at kind of the electromagnetic spectrum from our sun. And the sun, of course, emits all wavelengths, but its concentrated emission kind of roundabout in um, the wavelengths that we are sensitive to, visible light. And that has to do with its overall energy profile. Basically, every object, depending on its temperature, emits light. Us humans are lower temperature. We tend to, than the sun, obviously, we're lower temperature. We tend to emit our energy in the infrared, but the sun is concentrated in the shortwave visible. But nevertheless, it has a overall profile which emits across the wavelengths that we see here. And then our Earth's atmosphere has a certain amount of opacity at certain wavelengths. So we have these atmospheric windows that I mentioned before. And so we can take advantage of those and tune our remote sensing sensors to the wavelengths that we want to learn about. And so visible light is a great thing, but also as we go into infrared or microwave sensors, they can be used to look at different parts, different things. If some parts of the atmosphere are opaque to light, well, then we could use those parts of the wavelengths, to look at what's going on with the atmosphere and learn about that rather than the surface of the Earth. Okay, so radiation budgets and remote sensing. So solar irradiance is the light received by the surface from the sun, so watts per square meter. Radiance is equal to the emitted plus reflected light to the sensor. So what is the energy in watts per square meter of light that the remote sensing sensor felt? Reflectance is the radiance divided by the irradiance. So basically it's a ratio of what the sensor saw relative to what the sun emitted to the Earth's surface. And then absorption uh, is light energy taken in by an object or substance. And it may be absorbed by the surface itself, transmitted to a different energy source, or by the atmosphere. And so the overall emission is light emitted from an object, and that is proportional, as I mentioned, to its temperature. And so when we measure things with passive remote sensing sensors, these are the properties that we are dealing with. So on this graphic here, you can see solar irradiance and daylight sensitivity in the dashed line. So solar irradiance is the amount of light coming from the sun, or energy that reaches the Earth's surface. Okay, so did I say that right? So light received by the surface from the sun. And so we can see here, pulling out the visible light, we can see that the solar irradiance is strongest, as I said, in the short wave visible. And then as we go into the short wave infrared, it tails off. Okay, so our eyes are nicely attuned to basically what the sun is providing the Earth's surface, which makes sense. But all these other wavelengths are here on Earth, and we can use them quite smartly. Okay, so what can we use these different wavelengths for? And these are only examples. There's many other things. So ultraviolet, which is even shorter wave than the visible, we can use to study ozone in the Earth's atmosphere. Near UV, so basically that's between visible and ultraviolet, or kind of on that boundary, is used to study atmospheric aerosols. The visible light has many applications, often to kind of do things like spying on the surface of the Earth, so spy satellites, or just visible observations. Near infrared, so as we move towards the infrared and long wave visible to near infrared, vegetation is strongly emitting in these patterns, as potentially are animals. And then shortwave infrared can also is kind of very discerning for looking at other types of plants, and as well minerals. So if we have data from shortwave infrared, we can potentially start to do geologic mapping from remote sensing. Thermal infrared, of course, it is measuring heat, and so we can extract temperature. We can easily identify fires, identify active volcanic activity. Microwaves can be used to monitor atmospheric water content, which means that the atmosphere is pretty opaque to microwaves, but therefore we can learn about what's going on with the atmosphere. Microwave can also be used to, with kind of an active sensor, measure land heights, potentially track winds, and measure changes in the Earth's surface, land deformation, using radar, essentially. And then radio waves are useful for looking at things like sea ice and to study the ionosphere part of the atmosphere. So brief history of remote sensing. So way back in the 1600s, we had magnification of distant objects, spyglasses, monoculars. First photographs, early 1800s. Aerial photographs from balloons began as recently as the 1850s. People are still using these technologies today. Widespread aerial photography missions came about in the early 1900s, 1920s, 1930s. In World War II, air photos were used widely for military applications, high altitude flights over enemy terrain. First satellites coming into play in the 1960s. Satellite and airborne remote sensing systems, the Landsat system, which is quite famous today, began in the 1970s, Landsat 1. From the 1980s, Landsat TM, Spot, AVHRR were some of the systems that come into effect. In the 1990s, we have airborne digital remote sensing systems. Radar becomes more proliferated, and a lot of old remote sensing done by military was declassified as satellite remote sensing became so much better and much higher resolution. And so that means we have a lot of historical remote sensing that we can access through those older military declassifications, which can be quite useful for learning about landscape change. Okay, so in the 2000s, we had then an explosion of new satellites and improvements. Light became widely available. And in the 2010s, we've basically been building on the spatial and spectral resolution. So being able to start to measure things the same way, but at a much greater detailed scale, both in spatial scale, but also in wavelength scale. And so we can kind of fine tune how we interpret what's on the ground because of that spectral resolution. Yeah, and then of course in the 2010s, everybody's got their own drone, and so we can deploy these really widely and collect all kinds of data. We don't have to be reliant on big governmental missions to do remote sensing anymore. Okay, so a couple of instruments in space that we want to mention that were funded by NASA. Land, sea, atmosphere, ice, and space. These are part of the NASA mission, is to monitor the Earth's systems. It's not all about other planets. And so they have the Landsat mission, which has developed with time, but it's primarily after understanding natural resources of the Earth, including vegetation, rocks, i.e. geology, locations of water, and what is the land cover overall. And then MODIS, and including Terra and Aqua, as you can imagine, one is to look at the Earth and one is to look at the water, is great for measuring large-scale changes in the biosphere, global carbon cycle, on land and in the sea. These two systems are quite different from one another in terms of spatial scale. Landsat pixels are about 30 meters on a side, so we can look at pretty detailed things, including like somebody's yard, whereas MODIS, I believe the uh, spatial resolution is on the hundreds of meters. And so it's not good for looking at somebody's yard, but it is good for looking at broad scale atmospheric phenomenon, snowfall, um, carbon emissions, things like that from a whole region. And I think the return time is much higher on MODIS, i.e., you can get images over the Earth every day, whereas Landsat, any given one spot, only is revisited every 2 weeks. So what do we do with this data? So if we know kind of how different elements of the landscape emit light, we can interpret what's on the ground as some sort of spectral mixing. So here in B, we see different things. So chaparral, vegetation, has one kind of signal. So here we see wavelength on the bottom and reflectance here. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. Oh, is that not quite right. I guess the scale's not quite right. These are all offset from each other. So the space in between here is 0.1. Sorry about that. So the reflectance of the chaparral is very strong in these wavelengths, about 1 micrometer. Um, and it's less strong if we look at serpentine, which is the rock underneath. And so you can see there's also peaks and troughs in the reflectance of different wavelengths of the grasses, whereas the rocks kind of have a more smooth trend over there. And so then if you mix these things together, then we see kind of a signal of that mixing, which will be a kind of combination of these two spectral curves. And so we can model that and then potentially pick out in the landscape what is the land cover? Is it fully covered by chaparral or grass or serpentine, or is it some mix of them? And so this takes a lot of quantitative work, but it's something we can do, and then therefore kind of eliminate a lot of the need for intensive field work. So Landsat and is quite good because it's at a spatial scale that you can even monitoring agricultural regions. And so we can watch food resources, water, forests, and other natural resources at a global and regional scale. It has 30-meter pixels for most bands. Bands are kind of regions of wavelength. And so you can see there's some width to the bands. That's why they're referred to as bands. So band, um, well, this is the wavelength axis at the bottom here, and then atmospheric transmission at the top, sorry, in the y-axis. And so you can see that curve through here for the atmospheric transmission. And then the Landsat bands are here. And so MSS was the first Landsat mission. Um, and there were several of those. And then in Landsat 6, it's TM, I believe stands for thermal and microwave. So we start to get these other bands that are outside of the visible to near infrared. And then that progresses more with Landsat 7 and Landsat 8, where they've fine-tuned the bands to look at different things and added in some other bands to look at atmospheric properties. And so, yeah, so there's a history kind of things going on, and I believe Landsat 9 should be up and running, although I don't have that up here now. Radiance versus reflectance. What does the data mean? So Landsat data are often given as 8-bit digital numbers, like a photo. So 0 to 255. This scale is basically scaled to the amount of light hitting the instrument. It's okay. This saves space. It's not a very intensive data format. 255 is like maximum intensity of light hitting that sensor. Radiance is measured in watts per square meter, and these are just digital numbers. And so that is clearly not what's shown here. So in order to convert these digital numbers to radiance, if we want to get at that quantitative value, then we need the metadata and we need to process it. And there's tools to do that within a lot of remote sensing platforms. Reflectance is simply a ratio of the light that was emitted from the object that you're sensing relative to what originally hit the object from the sun. And this can give better information about the object, but it requires you to correct for the sun angle and the Earth-sun distance. This information is provided in the Landsat metadata and is easily detected and handled using remote sensing software platforms. Once we've processed things in an appropriate way, we can start to manipulate the signal. And so one thing that we can to learn about specific things. If we know about how particular objects in the landscape reflect light. So one common thing that's very powerful and maybe a first thing that somebody would learn about in remote sensing is vegetation index, such as normalized difference vegetation index or NDVI. And basically what you do here is you calculate it by taking values of the near infrared uh, light coming to the sensor, subtract from it value in the visible light, and then divide by near infrared plus that same visible light. This will yield values of -1 to 1. And areas above 0 would be areas that have actively photosynthesizing plants present. Because basically, photosynthesizing plants are strongly absorbing light in the visible and strongly reflecting or emitting light in the near infrared. So generally this will have values greater than 0.3. So for example, uh, if you had a value of 155 for the near infrared, you subtracting 23 for the visible, because it's absorbing and not emitting in the visible, and then divided by 155 plus 23, you see you get a value of 0.74, which would mean, yes, it's photosynthesizing. So it's green, healthy vegetation. Bare earth and other materials doesn't absorb visibly light as strongly, visible light as strongly, it reflects. And we can see this, rocks can be shiny. Um, and they also are less emitting in the near infrared. So they generally have values of less than 0.3, often negative. And so then we can create maps like we might see here near this lake, which can show areas of a lot of plant health and areas that might not be as healthy. Okay. So yeah, I guess that's what we'll say about that for now. So we can do this at the global scale, maybe using a satellite such as that has very low spatial resolution, can go across the whole country within a day and see patterns of plant foliage, or we can look at a field and see where plants are healthy or not. And so here you can see somebody's done that, and you can kind of sense the patterns of plant health in the field. Um, in some areas, maybe it's just tied to moisture content. Low areas have more moisture and are doing better. In areas where maybe there's less, kind of more soil that's kind of in a positive relief, it's kind of drying out and doing worse. But we can do this at really small or large scales. Geologic bands can be quite useful as well. So um, there's no such thing really as geologic bands. Sorry about that. But different ratios of the Landsat bands can be quite useful. So 5 versus 1, 5 versus 4, 7 versus 3, and 3 versus 2. Really what we're doing when we're using these band combinations to try to look at geology is we're looking at hydrous mineral phases, which are related to the weathering of rocks. Um, Weathering products of silicates are clays, and those clays have very different emission spectras. And so we can kind of distinguish one type of clay versus another, and they have some association with the parent rock type. And so we can easily map geologic difference, essentially. And we can start to guess at what the type of rock might be. But to get truly at the different types of rocks, we want to validate it with going into the field as well. But you can probably see that here in desert terrains, like we see here, we can create these really wonderful false color images, which are representing differences in geology and surface materials very well. Active sensors such as INSAR can be really useful. And INSAR is basically kind of sending uh, It's called interferomic synthetic aperture radar. And so it basically goes over, flies over the Earth, and is beaming down a signal and measures the transmitted time for the signal to reflect back. It passes over the region with a similar look angle, and if there's any difference in that look angle distance to the ground, it will measure that very precisely. And so we can measure contours of ground deformation by these interferograms. And so where you see these kind of rainbows of bullseyes coming out, that's areas where we've got ground deformation up or down. They're essentially bullseyes of that change. It could be positive or negative, um, but you can process that into basically areas where the ground has moved up or down or away horizontally or um, from the sensor. And so the trick, of course, is that we need to know the look angle of the sensor and the flight path. And if we're trying to interpret tectonic deformations, um, understand the geometry relative of like how fault moved or a magma body intruded relative to that look angle. Um, Shuttle radar topography mission was this active band radar that was flown on the shuttle in the 1990s, the NASA space shuttle, and made the first kind of near global um, digital elevation model for the Earth. And so this was really powerful data at first off, and it was once only given at 90-meter data for the entire Earth, although 30-meter for the US. Basically, that was trying to keep the data at a high resolution out of other countries' hands that hadn't paid for it. But today, all that data is available at 30 meters everywhere. And today, we can get much higher resolution topographic data from satellites using satellite photographs rather than radar, um, getting down to the meter scale. LiDAR is another form of active energy where you have these laser pulse returns. So if you could fly a plane or a drone over with a LiDAR source and sensor, sends a laser pulse to the ground. Um, it has some width to it. And so if you go through things like a tree, some of that light will hit the different parts of the tree, and there'll be returns that come back quickly. Other parts will get further down, and then we go up a different part of the canopy, and then we presume that the last return will be a signal from the ground. And so the cool thing about LiDAR is essentially you can remotely sense the tree canopy as well as the ground surface. And so it can be used for people that are interested in ecology, botany, or it can be interested in geomorphology and geology. Oh, the other cool thing I'll say about LiDAR is it actually penetrates clear water pretty well, and so it's also used a lot by NOAA to look at changes in shallow coastal topography, even below uh, the high water marks. So looking at beach change after storms. So MODIS, we mentioned earlier, has many bands, which is really cool. And so this table over here, sorry, it's a little bit uh, degraded, but it shows the different spectral ranges in nanometers of the bands, their ground sampling interval, i.e. pixel size. So land and cloud boundaries, these bands are 250 meter pixels. Land and cloud properties are at 500 meter pixels, and thermal properties, and these other ones are at 1 kilometer pixels. And so at such a big pixel area, you can see this is one scene. We can cover the Earth very rapidly over a bunch of flight paths and get high rates of return on the imagery. So we can track storm systems moving um, across the Earth, which is quite cool. But you can see that it has many, many more bands. Um, than Landsat. And so you can get really detailed kind of changes and looks at the ocean, at the atmosphere, at the land, but you can't look in detail because of the high pixel size. So anyways, all this has really, MODIS can have really great Earth system science applications. We can track fires and the thermal signal from those, as well as the smoke clouds. We can potentially track algal blooms off shore in the ocean, potentially track sea currents, track sea surface ice and the relative temperature of that ice, kind of predict when it's breaking up, things like that. Really cool stuff. So you're probably seeing that we have several dimensions to worry about for remote sensing data. And so that can be kind of the ground sampling interval or the XY pixel sizes. And so this graphic, and then also the spectral bands and what bands or wavelengths it's looking at. So this graphic here shows a bunch of different satellite systems. Ground sample index very low to 10 centimeters, 1 meter, 10 meters, ground sample interval of 100 meters or a kilometer, and then spectral bands. So MODIS shows 7 bands. Is that right? It actually has more than that. So I'm a little confused about that. So, oh, this is sorry, these are different parts of MODIS. So MODIS visible near infrared, MODIS visible shortwave infrared, and microwave infrared. So different parts of MODIS have different bands. Where's Landsat? So we would expect it should be, yeah, right in here. So 8 or so bands. Newer ones have more. But you can see there are some satellites that have much higher ground sample intervals, so smaller values here, like QuickBird can make pixels less than a meter. So these are getting to be like what we would expect from science fiction satellite spying technologies. And indeed, of course, the military has satellites that it's using all the time to look at things at really high resolution like this. But you can commercially access some of these satellites. And so if you want to have returns on the landscape at a high resolution, you can do that from satellites. So you can see QuickBird and the visible to near infrared for vegetation monitoring. You can get it at about 1.5 meters at any spot on the Earth, pretty much. So we can go pretty detailed, as you can see over here, with the Great Pyramids and what we can see from a satellite, very detailed imagery. Or we can look at details of maybe some remote ecosystem, like we see here in this atoll with these wonderful lagoons and reef environments, and we can map changes before and after a storm using one of these satellite systems without having to go there. Or we can monitor what's going on a volcano in a really high resolution, which would otherwise be quite dangerous for both equipment and people. And so we can look at things differently in satellite remote sensing, as we've been seeing, but these are some examples of that. So one thing we do a lot is what's called false color imagery. So where we basically, we are looking at images in red, green, and blue, and we may be processing data in different wavelengths. Visible is one thing, but it could be near infrared, microwave, etc. But we have to, in terms of our visual interpretation, either look at the numbers or we can look at those other wavelengths, but colored in a false color of the wavelengths we see. And so here we can see these false greens along the Mississippi River Delta, and not showing exactly what this one is showing, but it might be showing vegetation health, photosynthesis, or something else. But we can tune that however we want. I assume this one up here, the red, is actually showing areas of uh, biological productivity, maybe through photosynthesis, because it looks like the red is in high topography. And so I assume that's where there is vegetation actively photosynthesizing in this image. Um, and that may be the case of what's going on here too, although I may be looking at something else. Another cool thing you can see is a lot of detail in the oceans. And so that can have to do with kind of marine activities as well, biologically. Okay, so that's our overview for kind of remote sensing. We will have a practical lab on this when we come back from fall break as a part of that lab set. Okay, so thanks for watching your video. Make sure to also complete your exam number 1 for the remote sensing class and work on your journal, which asks you to come up with some ideas for your final projects in the class. If you have any questions, just send me an email while I'm at the conference. Okay, take care.